Hey everybody, John Shutsky here with BSE 508, and we're here to talk about a really critical conversation on senior design, and that is product or project design specifications. Now, I want to just caution you here, or just give you a little bit of a pointer or a hint. I'm going to be using the words product and project interchangeably. I think a lot of you, when you think about a product, you might think of something like this TV remote control, and this is obviously a product. It's something I can pick up, I can hold it in my hand, I can manufacture it, I can ship it around the country. So that's a product. On the other hand, there may be things that you work on that are more project oriented. So it may be a wetland project or some other environmental project. I actually view those both as products. If I'm designing a wetland, obviously there's a design that's going to come from it. There's probably going to be a document or a computer file or a set of documents, and those really are part of your design. That's part of your product. So I am going to use those terms very interchangeably throughout this conversation, but we're talking about PDS, or Project Product Design Specifications. Let's talk a little bit about kind of where we're at right now. We're about a third of the way through this semester, and you've done a lot of stuff. I'm not going to go through all of these in detail, but you've been collecting and analyzing and summarizing a lot of information. You've been doing a ton of research in all of these different areas. And one of the reasons why I have you doing that is to help you ultimately develop these project or product design specifications, which will really be the real heart, the real beating heart of your project. And this work that we're having you do is also helping you to really get a good understanding for what is this thing you're working on? Why is it important? What's the true need? What's the ultimate goal of your design? Every design project ultimately needs to have a goal in mind. And it's also important to be able to go back from time to time and relook at all of this work you've done and all of the data that you have collected and analyzed, because sometimes you get in the middle, especially when you get into 509, you're going to get those first couple weeks and school's going to be going on and you'll be a little bit overwhelmed. And sometimes you're going to need to go back and reground yourself and say, now, what is it we're working on? And why is it so important that we're working to develop this design or design this particular prototype to solve a specific problem? So that's kind of like where we're at this point. And now what I'm going to have you do is to begin to think about these product design specifications. And to be able to do that, I want to just introduce an idea here that a lot of you have probably heard about before. And it is an idea, it is a concept that is central to design and design thinking. And the concept that I want to talk about is that design thinking is an interesting combination of both divergent thinking but also convergent thinking, and both are needed. They're needed at different times and different stages during the course of your project, during the course of the design process. So what is divergent thinking? So divergent thinking is when things diverge, when they spread apart, when they move apart, when a road forks out into two different branches. That is a divergent, it's a divergent road. It's a road that forks out in multiple directions. And the idea here is that if you're going to be creative, if you're going to be innovative, if you're going to come up with lots and lots of ideas, you need to be able to practice and effectively perform divergent thinking. An example of this is when you do brainstorming. I'm guessing some of you have done brainstorming in the past. Maybe you're working on a project. Maybe you're thinking about going on a trip, having a party, something like that, and you want to think about, like, what might our themes be, or where might we go on the trip, or what might we do to what topic might we explore in this particular project. And so with divergent thinking, you're asked, or with brainstorming, you are asked to get as many ideas out as possible. Bring all the people who want to be part of this. Let's get ideas onto the table. Let's write them down. Remember some of the ground rules of brainstorming. There's no such thing as a bad idea. Everybody's ideas count. No matter what we think about it now, let's not judge it, but let's get them down onto paper, because that's where a lot of the creativity and innovation is going to happen. However, and you're going to do that with 508, 509, However, there comes a point when you need to move from divergent thinking, and it's almost like you need to throw the transmission in reverse and go the other direction towards converging. And when you're designing something, you need to begin to converge to make decisions and to choose from among a whole bunch of different alternatives. And eventually, that's how you narrow down that final focus. And by the way, convergent thinking versus divergent thinking is also something that I think is a skill that we can all develop and use in other aspects of our life as well. But the question is, how do we do that? How do we take all of this brainstorming, possibly like weird, wild, wacky ideas, and begin to narrow those down into something that is actually going to lead us toward a final design and toward a final solution that'll meet that need that we've worked so hard to define in the first third of BSE 508. And the key to doing that, the filter for doing that, is your project design specifications. It's like a filter. It's like a coffee filter. It's only going to let certain things pass through, and it's going to be based on the work that you do to develop and really carefully think about, articulate, write down, and communicate your project design specifications. So it's the filter that you'll pass all of your awesome ideas through. It's the beating heart, as I said, of your design efforts. It will require all of this research and understanding that you've been doing, all the stuff you've looked at so far. It will include a list of things that you absolutely have to have, and also things that might be nice to have. And I'll come back and talk about that in a minute. And again, this idea is this filter will help you go from wild, wacky, creative, brainstorming, all ideas count, everything on paper, long lists, to begin to narrow that funnel down towards something that is more manageable, more focused, and something that will help you make final decisions. So you're going to have a bunch of project design specifications. I would say that most projects are going to have somewhere between 15 and 30 project design specifications. You might want to remember that number, because when you do your progress report and you're doing that progress report together as a team, I'll be looking for the project design specifications. It'll actually count for more than any other part of your progress report as we move to the end of 508. It's going to have these 4 elements. First of all, it needs to be as specific as possible. And it also needs to be precise if that is possible. And it should be quantified. So let me just give you an example. If I'm going back to my example of my TV remote control, if I say that one of the project design specifications or product design specifications is that I need to be able to control the TV from a long distance away, that's not good enough. I need to be able to say that this is going to send out a signal. We haven't yet decided what the signal is going to be, but this is going to send a signal out towards our television, which can be as much as 5 meters away, roughly 15 feet. It needs to be really specific. Just having, it needs to go a little ways, just try to get it across the room. Well, across the room in one room might be 15 feet, and in another room, it might be 50 feet away. So you need to quantify, and obviously that means providing the units associated with the quantities that you're providing. A third factor, a third criteria for good project design specifications is that they should be backed with evidence or reasons. And again, the evidence or reasons are why we're having you do the research, the annotated bibliographies, looking at standards, reviewing patents, looking at the current state of the art, looking at past or prior art in patents, and also talking to the people in your market. And that includes not just talking to one customer or just talking to your advisor, but talking to a bunch of people who are ultimately going to be the people who benefit from your design. And then the final thing, and I mentioned this earlier, they have to contain words that show the things that are absolutely required and things that might be optional, because it's those optional things where you might have some additional flexibility. You might be able to make some choices that are a little bit different. And those might also be the areas where you can display a little bit more of your innovation and a little bit more of your creativity. So we're talking about these critical words in a product design specification. The words where you don't have any choice are things like must not, required, shall not. So here we are right now in 2021. Yeah, we're in the midst of the pandemic still. Hopefully, we're winding toward the end of it. And maybe for some of you, when you watch this video in a future year, you'll think back and you'll like, aha, remember that. But right now in 2021, if somebody tells me here at the University of Wisconsin, you must have a clean COVID test before you can go into one of our university buildings, must, like there's no option with that. You must, or you must not go in a building unless you can show that you have a successful clean test. So the word must or the word shall, another way of saying that is you shall. If my dad, back in the olden days, if my dad would tell me you shall do it, I better do it. I did not have a choice. It was not optional. Versus some words where there is a little bit of limited degree of choice or a limited degree of flexibility. Should, if somebody says, and this is the way it was here in the fall, like back in October, like, yeah, you really should think about getting tested once in a while for COVID. Like, yeah, it's kind of optional. Or you shouldn't really, think about going out to eat or whatever. That's different than saying you must or you shall not. So knowing the words, being really precise, not only with your numbers and quantifying your design specifications, but also being very precise with your words is also really crucial. Let me also say, this goes back to our conversation a couple weeks ago on design standards. Now, if you go back and look at some of your design standards, you'll notice that they're very precise about using must and shall and should. And shall not. They're very, very careful because those engineering standards, if they are applied in a legal situation during lawsuit or when a project designer is working on their project, those standards also, those words are also very critical in the context of engineering design standards. Just 4 examples here really quickly. Let's just say that I'm taking in raw materials into a warehouse. If somebody says, yeah, those incoming materials, they may be inspected before they're accepted into the warehouse, that's very different than saying those incoming materials must be inspected before they're accepted. Very different meaning, very important to know the difference in these various words that are found in project design specifications. Let me give you an example. So this is from an actual project from a few years ago. I do want to credit one of our former professors, Dr. Dave Bonhoff, who's now a professor emeritus. He used to do a lot of work with what we call post-frame buildings. These are really common in maybe small-scale industrial sites, really common on farms. And a post-frame building typically has posts, vertical posts, that are placed onto a precast and actually literally dropped into a hole into a concrete footing. These, I'm going to refer to these as either concrete footings, or some people sometimes refer to these as cookies. They're not really a cookie. I mean, they're a round shape like a disc. But these things are heavy. They weigh typically anywhere between 180 and maybe as much as 300 pounds. The problem is, well, let me say the benefit. The benefit of the cookie, the benefit of the footing is obviously they form a foundation for those posts. Especially on loose soil, they spread the force out over a larger surface area. So there's lots of benefits. The problem is, you can think about this. You have a 4 or 5 foot in diameter hole, and you're having to drop these discs into the hole weighing 150 to 300 pounds. You better make sure you do it right. When you drop it in there, you need to make sure it's level. It needs to go in square. If it's off center a little bit, or if it's dropped in not level, you're probably going to do damage to the side walls of the hole. So it creates all kinds of problems. And if you scuff the side wall, you're going to also crumble dirt and sand down into the hole. And then chances are that cookie is not going to land level. And it's really difficult. And it's also very difficult to get it back out of there once it's been dropped into the hole. So the idea would be a design that would drop this in a fashion that would be replicable, that would be sustainable, that would be safe, that would be functional, and actually in the end be exactly where you want to locate this cookie. This is was a real problem in the construction industry. So the team that was working on this, I'm not going to read this whole thing, but they went out to construction sites, they interviewed people, they looked at how the construction industry was currently doing this, and what they determined was that there's definitely a need for this, and there's a need to be able to do it without some type of a powered piece of equipment like a skid steer loader or a backhoe, or that's the way they'd been doing it. And they were also requiring 2 operators. So they wanted to be able to do it hopefully with just one person. So they developed a statement of need. I'm not going to read the whole statement of need, but you can see here. Also at the bottom, just note that it was connected to safety, to cost, to the time management, the fact that on a construction site, time is money, right? And also making sure that they wanted to do the job right so that the building would be functional at the end based on the way these footings were dropped in. So they developed a design goal, a device that would enable a single person using simple, non-powered, non-self-propelled equipment to move these footings into place, to lower them into place. And they wanted something that would provide a documented savings in labor, and then also to ensure the consistent placement of these footings. Again, from a functionality perspective, that's really, really important. So I'm not going to go through each of these. There are 10 design specifications, but you'll notice some things. In these design specifications, we have the signal words or the words that designate whether these are absolute must-have specifications or are these things that would be nice. Again, my example, must handle a concrete footing with a diameter between 14 and 34 inches. It's like, yeah, I don't really have an option. This specification does not make it optional. It must have the ability to handle a piece of material of those dimensions. However, there's this other one, number 2, that says, well, it shouldn't exceed 100 pounds mass when unloaded. Well, that to me says, it'd be nice. It probably shouldn't, but if it ends up weighing 125 pounds and yet it performs all of the other duties and it meets a lot of the other specifications, this might be one where I have a little bit of flexibility. The 100 pounds still gives me a pretty important guideline to shoot toward, but it does provide me with some flexibility. So as I mentioned, there are 10 of these total. Number 7, I want you to just note, material costs should not exceed $150. Number 9 and number 10 are important because they deal with very specific standards. In this particular case, OSHA standards. So our design specifications also need to incorporate engineering standards, regulations when they are applicable, and other things that are based on code, legal needs, some of those sorts of things need to be part of your design specifications. In the end, this was their final product. It was very successful. It worked exactly as they had designed it. You'll notice that it uses like a DeWalt power drill, so something that you would find, that's their main power source for lowering this cookie down into the hole. You can see it's big enough that it spans the hole. It looks like a wheelbarrow, can probably be moved from hole to hole across the site. The other thing about it is it used a 2-stage planetary gear, which optimized the speed and the capability, the torque that was put out by the drill could handle this particular system. And one of the problems, even though it was super successful, that 2-stage planetary gear was quite expensive. So you remember that there was a design specification that said that the cost shouldn't exceed, I think it said should not exceed $150. Well, the planetary gear by itself exceeded the price of everything else, or the cost of everything else on this particular design. It was quite a ways over that $150, but because it was so functional and worked so well, the group considered this to be a success. And part of that was because they were very careful when they laid out their specifications to use the right words. Now, you don't want to go back and fudge the words in your design specifications, but think carefully about, is this a must? Is this a should? Is it a shall? Is it a nice to have, or is it something that is an absolute requirement? There's the planetary gear. Here's what that particular device, and remember there were all kinds of parameters in there about what it would look like, how heavy it would be folded up, unloaded, where it would be stored. In this case, it would also fit into the bed of a pickup truck on a construction site. And again, a lot of the actual design decisions were predicated on their project design specifications. I think I might be going in the wrong direction. So let me just conclude by talking about a few things. There are different categories of design specifications. There are things related to the function. Okay, so function relates to the flow of energy, how this thing needs to perform, what does the flow of information look like, how about the flow of materials, capacities. In agricultural systems and also in environmental systems, flow capacities become really important. It could be material flow, it could be water flow, it could be other mass flow. Also the operational steps, the operational sequence. We also have human factors and safety requirements. I'm not going to go through each of those because I've got another resource I'll point you to here in a few minutes. There are also physical requirements. So note that on that construction site concrete footing mover, there were all kinds of physical requirements: the size, the weight, the footprint, how big it would be folded up, how heavy it would be. So lots of different physical dimensions and physical requirements. We also need to think about product reliability. Like, how dependable does this thing need to be? How long is it going to last? If this is a device that's going to be used on a construction site, probably 200 days a year, 220 days a year, is it going to last a year? Is it going to last 5 years? Is it going to like, how many cycles is it going to withstand? So that's going to help you to choose the cable for raising and lowering. It's going to help you to determine a lot of the different factors. And then also when we look at environmental projects, we need to look at the reliability with respect to loads and events. So if we're designing a dam, if we're designing a runoff structure, we need to be thinking, are we dealing with 10-year storms, 10-year rainfall events? Are we dealing with 100-year, 1,000 years? And in a lot of cases, those kinds of specific specifications are dictated by standard or by some of the things that we've talked about previously. And also, those are things that are really important to talk to your advisor about. We also need to be thinking about this product throughout its entire lifespan: shippability, maintainability, etc., all the way down throughout the lifespan to the time we get rid of the product or retire it. Disassembly, recycling. Is this something that can be landfilled? Does it have hazardous waste associated with it? And again, how are we going to handle it during its entire life cycle, including the very end of this product or system's life? All kinds of other things: resource concerns, the time required, the cost. That includes not only the cost to purchase, but also the cost to maintain it, and like annual maintenance and upkeep costs, capital costs, equipment. Again, as I talked about, applicable standards, codes, laws, rules, regulations, and then also thinking about what is the impact on the environment. So our products or our systems oftentimes do not operate in a vacuum. We're oftentimes operating in a political environment, in a social environment, in a people environment where you might have people, workers, people interacting. That's part of human factors. But then also the impact on our soil, our water, our air. And now we need to think about the impact of our products on the climate as well. And that's becoming a big driving force with a lot of the design work that's happening out in industry. And then finally, we need to think about manufacturing requirements. So here in 508 and 509, you might think, well, I'm not going to really be involved in manufacturing. Well, you actually are. You're going to be manufacturing, for many of you, you'll be manufacturing a prototype. So this is kind of a mini case study in that, because you're going to be manufacturing your prototype in the BSE laboratory. So you'll probably want to be having conversations with people like Cody who is our shop supervisor, manager. He's the main staff person in the shop and in the laboratory, who can really help you think through, how are we going to manufacture this? Are we going to 3D print it? If it requires metal, do we have the types of tools and machining equipment that will be required? And all of that has to be talked about as you're thinking about these design specifications. So that is the overview on design specifications. And homework number 8, this is exactly what you are going to do. You are going to define and clearly articulate, in other words, spell out the design specifications for your specific project. In the module, I've provided you with a bit of a template that might be helpful for you to think about how you write these out for your particular project. So it'll be in the module. Let me just go through this here really quickly. I've got space for a project title, the goal of the project, and then I've got some examples, and these examples are under these headings. First of all, the category for the product design specification, the actual specification actually written out carefully with units, with the appropriate citations. If we're citing, we don't, like if we have to comply with a standard, we don't quantify the standard, but we need to say exactly what is the standard or the section of the standard that we're citing within the specification. Also, that requirement language, like I talked about, is this something that must, or is it something that may or should be? And then over on the far right, what is the documented source of the specification? It might be a research article, it might be a standard, it might be another specification. It might be the requirements put out by your advisor or by your client or by your customer, but you want to be as specific as possible so that there's a paper trail, so that you later understand, like, why is it that we came up with that specification for future documentation? But also, if you ever have to go back and revisit the specification, it'll give you that information that allows you to do that trace back. Now, I'm not going to go through each one of these, but I have like 2 examples here. I encourage you to look at these. These are examples from one of my projects from previous years. I've got one that's a safety standard compliance. I've got one that is connected to the power input, the functionality of it with respect to having a rechargeable battery system. And what would the specifications of that battery system be? And then down in the left-hand column are all of these specifications that you really do need to think about and consider. Again, everything from functional requirements, human factors, safety and health, physical requirements, reliability, life cycle, resource and economic requirements, manufacturing, standards and legal or regulatory requirements. And then this last one is other things that the customer might like. Things that might be good based on looks or appearance or style or aesthetics. So you can use this when you do your homework to spur your memory, to help you to think about and brainstorm, what are the specifications going to look like on your project? And that's what's really important, is you begin to think about this stuff, these specifications with respect to your project. Again, you're going to do these as an individual. You're going to have some commentary back on that particular homework, and then you're going to take this, work together as a team, and you're going to have a comprehensive set of design specifications. And so that as you go back, and remember, as you start thinking about and brainstorming and looking at all of these creative solutions, you might have 10 solutions that might form the basis for your design. The project design specifications will be the filter through which you'll run those great ideas. And then ultimately, by going through that funnel, by converging those ideas, you'll be able to make the decisions that'll allow for a successful design and a successful project. And I can guarantee you, these are the kinds of skills that real world, real life engineers use every day. And the more creative you can be on the divergent thinking side, that's awesome. But also the way that you can gradually work this way through the decision funnel with your project design specifications, that's where the beauty is. That's where the art of design happens.